Let's do our next set of problems that use the log rule for integration, but these two use a trickier method that you probably haven't done for quite some time. So what we have is 2x squared plus 2x minus 3 divided by x minus 9. So you could try to do like a u substitution, say, well, u is equal to x minus 9. And then man, if you did that, this is possible to do. But you would have to say, all right, well then that means that x is u plus 9, and then you would have to factor all that out and combine that and create a sequence of integrals. And that's okay to do. In fact, I think I might do that. I think I'll do that for this one, but then I'll show you the long division method here. So, yikes. So what we're going to do is we're going to say, and this is going to be kind of gross. I wouldn't recommend doing it this way, but it's possible. You can say u is x minus 9, so x is u plus 9, so du is dx. So then we're going to go all the way through this. We're going to say, all right, this is now the integral of 2 u plus 9 squared plus 2 u plus 9 minus 3 over u du. So then I need to factor that out. It's going to be 2 u, or multiply that out, u squared plus 18u plus 81 plus 2u plus 18 minus 3 over u du. Now I'm going to skip a couple of algebraic steps just to combine it all into one. I'm going to get 2u squared plus 38u plus 177 over u du. And then I can split this up into 3 separate fractions. That'll become 2u plus 38 plus 177 over u. So not really 3 fractions. So then we can then evaluate this to say that is u squared plus 38u plus natural log, or 177 natural log of u plus c. Now I didn't do it that way normally, so let me check my cheat sheet, make sure I've done this correctly. Alright, I've done something wrong. So I should have well, maybe I haven't done anything wrong. Maybe I haven't. So u is x minus 9. So then I actually have to go back. This is where this gets gross. I have to do x minus 9 squared plus 38 x minus 9 like that. So that becomes x squared plus 20x, because that's minus 18 plus 38. And then I get plus 81 minus whatever, so that's 270, 312 minus 81. Oh, haha. Alright, so this is kind of the neat part. So I'm going to point this out here. So that whole point of getting positive 81 and then subtracting that 270, blah, 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 all those are just numbers, right? So if I add them to some arbitrary constant, they all get sucked in. They're just some number. So you don't actually have to worry about that with the plus c. That's still pretty gross, though. I wouldn't recommend doing it that way. You can. Not all problems are going to be able to be worked that way, really, but that is a way to do it if you just really hate what I'm about to do over here. So, you do you. So over here, we're going to revisit an old concept called long division of polynomials. And you may not remember how to do this, but it operates exactly like long division for real numbers. So what I'm going to do is I'm going to say, okay, well, if I were trying to divide x minus 5 into some polynomial of 1x cubed minus 5x squared plus 0x plus 7. So you kind of have that same placeholders, but for the coefficients instead of the digits. You say, all right, what do I have to multiply this by to get x cubed? So you always look at the first thing. You say, okay, well, that would be like x squared. So then if I multiply this by x squared, I get x cubed minus 5x squared. But then just like in long division, remember you multiply these two things together and then you subtract them. So these go away. So you have this 7 here. But there's nothing I can multiply x minus 5 by to get 7. So 7 is like my remainder. So in this particular case, there is a way that I could have done this that's a little cleaner. I didn't think about this at the time, but long division, this one I don't know that you would have gotten very easily with long division. Like in this one, if you do x minus 9, 2x squared plus 2x minus 3, you end up with an 2x, so that becomes 2x minus 18 x, 2x squared. When you subtract, you get a positive 20x minus 3. You do a plus a 20, you get 20x minus 180. And when you subtract, you get a remainder of 177. So that's why you end up with 2x plus 20 plus 177 over x minus 9 dx, which then integrates to x squared 20x 177 natural log x minus 9. So this way is much faster. But this way you could do it and you end up with x squared plus 7 x minus 5 dx. So that's fairly clean, but there's another way to do this, which is this is x squared x minus 5. Right? That if I factor out an x squared, I get x squared times x minus 5 plus 7 over x minus 5 dx, which gets me exactly that. So this is the same idea, but long division is kind of more of a guarantee on that. So then from here we can take the antiderivative. That's 1/3 x cubed plus 7 natural log x minus 5 plus c. So I skipped a step here. I went straight from here to here. Why could I do that? Well, A, it's because I've done this a bunch. But B, there's a pretty simple rule. Let's say that I have the integral of 1 over x plus a number. And it could be any number, and it could also be a negative number, so it could be x minus n. It doesn't matter. If I let u equal x plus n, then du is equal to dx. I get 1 over u du. So I get natural log of u plus c, natural log of x plus n plus c. So no matter what, if it's something over, if it just has this basic form, x plus a number, x minus a number, you can go straight to here. That 7 gets pulled out, of course, but that's the idea. So anyway, that's the answer we would get for this. That's the answer we would get for that. Again, that's way uglier. I think this way's cleaner, but if you hate long division, man, you just hate long division.